Good morning. There's a question for you. Yeah, the screen is still. But I wrote an angry letter. Let's see if it's going to help. Bulb A, the switch, and I don't have exactly same schematic, but very similar can be done. Let's see. Basically, we need a battery and a circuit which has two different sides, like this one, and so what did we do yesterday? For example, we can plug these wires, connect this well, this is how we did it yesterday, in parallel. And we know what's going to happen, but of course, a wire has no resistance at all, like the Democrats. So we can move a connection along a wire, still going to be the same parallel connection, and no one said we must use short wires. We can use long wires. It doesn't matter if it doesn't have any resistance. The length doesn't matter, right? Still same parallel connection. And again, that doesn't really matter where we keep it physically. And let's say left, right. So here on the right side, we want to do something. We add another bulb, close the switch, open the switch. Something, anything we want to. And the question is, how would that affect that bulb? And of course, it's good to have an intuition about circuits. Also, it's good to have the knowledge about circuits. And if we apply the knowledge, we can calculate. So you keep answering. So what can we calculate? Well, first of all, we can redraw the whole circuit, keep only elements which are active. And here all we have is this. We can call them A, 2, 3, 4, 5. So that's going to be A, 2, that's going to be 3, 4. The bulb number 5 is not in a connection because the switch is open, there is no current. And now it's very clear if the voltage is 120, all bulbs are identical. The voltage should split evenly here and here, 60, 60, and same here, 60, 60. But that's when the switch was open. And closing the switch means changing something here. Well, basically, we are adding an extra bulb. And this part has been done yesterday. Yeah. If we cut wires over here, this is a problem we have solved before. We know what should happen to the brightness of each bulb. We know what should happen in general. So, and come on. I can add this bulb in parallel to this one. I can add this bulb in series to this one. Yeah. Now the dimmer. Did it affect the brightness of this bulb? Not at all. And it couldn't, and it shouldn't, and it wouldn't, and it isn't. Because of simple reason. No matter what's happening on the right-hand side of the circuit, it doesn't have any effect on the left-hand side of the circuit. The battery provides the fixed amount of voltage across bulbs A and 2 together, and no matter what's happening here, we can, I think I have a picture later, so no matter what's happening with the bulb 5, it doesn't affect bulb A. Well, here, again, it's just a good practice to see if we can simplify the circuit to a single equivalent resistor. Of course we could. One step would be combining. So if we call them R, each bulb is just R. So what we have here is 2R and 2R here, which again physically is the same as just having 2R here and then another 2R here, because as we know, it doesn't really matter where it's physically located. We can just take this and bring it over here. It doesn't change a thing. But it helps to see what kind of a connection we have. Of course, in parallel. And in parallel, what's left is R. And now we can go backwards to calculate currents, voltages, like we did before. And again, this is a situation for the open switch. That's what makes it easy. So bulb A, nothing, does not change. And of course, let's just solve this case, which we have done before, right? So again, this voltage here and here should be equal to each other, and together should give 120. Now, this part, as we know, has the equivalent resistance of a half of the resistance of a bulb. So we can write R, 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 and for the whole thing, R over 2. And you see, still this voltage should be equal to 80, and this should be equal to 40, because there is no reason to have a different. Same relationship between the resistance and this resistor has a resistance twice of that, which means this resistor should have voltage twice of that, but together they should still give 120. What's the difference between having only 3 bulbs and altogether 5? That affects the current, of course. Now the battery supplies the current to everything. Well, the easiest way to see it is, again, just to calculate the equivalent resistance of the whole circuit, of the whole thing. So how can we simplify? Well, this is R. This is R over 2. And these 2 bulbs, when we move them over here, give a total resistance of 2R. And I've told it before many times, especially in PY 105. If you're not comfortable with using variables, you can pick any convenient number. The idea is simple. If the result doesn't depend on a variable, on the value of a variable, that means any value of that variable should do. So you could pick R equals 10, for example, or wherever. But in general, we always can do algebra. So what we have here is R plus so 1.5 R. And I should have drawn it better, and I will. Okay. So that's not very clear how they connected, but now 1.5 R and 2 R, now it is clear in parallel. So we can get down to the R equivalent. And what it should be equal to, same number as before. R equivalent should be equal to 1 over 2R plus 1 over 1.5 R. When I'm calculating the equivalent resistance of only 2 resistors, I always do this. It's 2 steps in one, adding inversed and flipping over. And so what is going to be? Well, first of all, it's going to be R times something. Times what? (1.5), that's 3 over 2. So 2 over 3, that's common 6. 6. 6 over 5, right? Over, no. The 2 is a common denominator. That's 3, 2 over 3. It's just an exercise for me. I'm waiting until you calculate. 3. So, no, it's 6. 6. So multiply by 2, that's 4. Multiply by 3, so 6 over 7. 6 over 7. That's it. Less resistance, higher current. Of course, when we didn't have those 2 bulbs, we had a certain resistance, but when we add something in parallel, we always decrease total resistance. So the current always goes up. Previously, yesterday, when we didn't have bulbs on the left, we had only current traveling like this. But now the current which goes out of the battery should split, but still should provide the same voltages on the right, which means the battery should supply more current than before. Any questions? Yeah.
So, did you, the R over 2 and R, did you put that flip into R?
Say it please louder.
Did you put the R over 2 and the R?
This is R. Yeah, I'm sorry for the drawing. This is R over 2. And they in series, so here I got 1.5, 1 plus a half. And technically, after we have combined those resistances into R and these in 1.5, we see that this, and this, all elements in parallel. Yes?
So the equivalent R is 6 over 7. The whole current is increased larger. But the current on the left side will still not change.
And you just make a statement. And yes, so but if you want to ask a question, you have to ask a question. You made a statement. I agree. Okay. What's next?
I was not sure about how the current distribution.
Well, you see, the battery generates, it travels here, split. It's a junction. Some current goes there, some current goes here. Then eventually there is a splitting point, and then they go together back in the battery. That's it. If you cut this wire, cut it, what's going to happen? You will take out a part of the circuit. And how does it affect the equivalent resistance? Only this part is left. And equivalent resistance of this part is actually higher than the equivalent resistance of whole 5 bulbs. So the equivalent resistance goes up. Current provided by the battery goes down. You can imagine all possible scenarios. Cut here, cut here, cut here, cut here. And for each situation, calculate new equivalent resistance, new current, new voltages. That would take a while. That's why I'm not going to do that. I just point at that possibility for you to practice and move on. Calculate the equivalent resistance. We just did it. And one more example, which I'm just going to go through, which we know what to do, which demonstrates a general strategy for any circuit. We start looking for anything which can make a circuit simpler. Here, what we see is, well, is this in series with this? No, there is a junction. Is it in parallel? No. What about this? Is this in parallel to this? No. In parallel, they would have both ends connected to each other. So all we see is here 2 resistors in series. As long as we have found something which has a name, series, you point the finger at it and we say, let's replace it with single resistor. So 220 and 250, 470. And then what can we do? We can look at the new circuit and ask the same question, can we simplify it? Well, now these two have become in parallel, so we can replace those. Now we look at this circuit and we ask the same question, can we simplify it? Yes? Now we see they connected in series. And it doesn't have to be that way. If we have like identical resistors, but if we have random number for each resistance, that's the only way to do it, because we cannot use any shortcuts. What do we do now? Well, now we just go backwards. We can always calculate electric current, and then we can use that new value to calculate something else like this voltage and this voltage. And then we can use that new value to calculate something else, etc., etc., etc. And this is a general approach which gives a general solution to any general problem. Again, you can try it out. You should get the same numbers. Any questions? Please. Do you have a question? Please ask a question. Why is it so difficult to ask a question? Just ask anything. Thank you for asking. Better? So this is what we have learned. And now I promised you 15 minutes. Yes?
The question we did yesterday
Yep.
Was the result of that that the resistance is raised the same amount by the temperature of this bulb, so it's still going to be 40 watts because of greater resistance? Never really put temperature into that problem.
Yes, because we don't have to, because we didn't need it. I just wanted to say that in general, if anybody asks you, what is the resistance of the bulb, you should say, well, it's easy to calculate, just 120 squared divided by the wattage. But you should know that will be the resistance, only the bulb, when it's been working for a while. That's it. Nothing else. Please. Yes?
So when you have a circuit that's like two circuits in parallel, like in the example that we were just doing, that's like with one battery that's 120 volts, would 120 volts be going like into each of the like...
See, I want to stop you right here. It's a very common misunderstanding. You say, voltage going, voltage just can't go. It doesn't go. Voltage is only is. So this is going, this is this. Going for what? For current. So electric current does go, travel. Electric current travel through. Through what? Through the bulb, through the battery, through the closed switch. Electric current travels through. The voltage is just here between these 2 points, or here between these 2 points, or we say, if you use slang, across that element. And every element is supposed to be connected to do 2 different points in the circuit. So that's why for the voltage, it's only here. Okay. Now you can say the question in a way I would understand it, because otherwise I wouldn't.
Right. So in the problems that we were just doing with the 120 volt battery, the electric current, like it doesn't split basically to have 60 ohm and 60 ohm on each side. It's like
You see, 60 is not electric current. 60 is electric voltage across a bulb.
But it's 120 on both sides if you have them in parallel.
Okay, I think it's a good, good place to review quickly a difference between the voltage and potential, because that's probably what we're talking about. 120 volts, this is EMF, that fixed voltage provided by the battery, no matter what is happening outside of the battery. We can add more and more and more and more bulbs to each side. It doesn't affect this number because it's based only on internal properties of the battery, well, ideally. And if we talk about voltage, that means automatically that we mean using a special measuring device we call a voltmeter. And a measuring device, a voltmeter, always has two electrodes. You can't use just one. I should have had it. Well, you had it in a lab. You have to connect both, otherwise you wouldn't read any number. So if you want to measure voltage, you have to connect those electrodes to 2 different points. And 1 point in a circuit always can be set to the zero potential, grounded. And all other electric potential can be measured relative to that. This will be 120 volt potential, because this voltage rises the potential due to the battery by 120. And potential, it doesn't travel, but it changes. How? Well, a wire doesn't change electric potential because a wire has no resistance. Exactly, again, like the Democrats. And this potential will be equal to 120. This potential will be equal to 0. And you see, I use the same letter, V, for potential. Now, potential here will not be 0, will not be 120. We can calculate it. And also there is potential difference or voltage across or between. Same here, potential, 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 another potential, another potential, voltage, another voltage, another voltage. And what I do really wrong, I don't use any subscripts. They look like all the same, but in reality they might not be. So we have to keep it in mind. They might be different. These symbols just represent a word. Potential, potential, voltage, voltage, potential, voltage, voltage, potential. And we now can read every number. We know this voltage should be equal to 60, and I don't want to go into this until anybody asks why. That's the voltage. What about this potential? Well, this number should be higher by 60 than 0. Or we can say this number should be lower by 60 than 120. No matter how you count it, calculate it, it's still 60. This voltage has been found 80. This voltage has been found 40. So if I ask for the value of electric potential here, yes?
The voltage difference on the left at 60, that's because it's the same R. If they had different R's, it'd be a different split of voltage.
Yes, exactly. In this example, all bulbs are identical, and this is a property of devices connected in series. If they connected in series, they share electric current. If they share electric current, the current is the same. So voltage depends on R. Same R, same voltage. Higher R, higher voltage. Lower R, lower voltage. Double R, double voltage. Half R, half voltage, like here. As long as they share the same electric current, the relationship between voltage and resistance is just proportional. That's it. Same R, same voltage, because same current. Now, here, what can we say? We can say this potential should be lower by 80 than 120, or this potential should be higher by 40 than 0. Of course, it doesn't matter how we get it, still 0. Now, actually, you have, I think, one homework problem where you needed to calculate potential difference between 2 points. Let's say this is A and this is B. And let's say you need to calculate potential difference between A and B. Only now you can do this. Because if you need to calculate potential difference, you literally have to subtract one number from another. That's what difference is. So before that, you need to know each number. But now we know this is 60, this is 40. So potential difference between these 2 points will be 20, which means if I take a multimeter and I connect one wire here and second there, I will read 20 or negative 20, but I always can switch it. Yes?
Can you explain the concept of grounding?
Can hear?
Grounding, and why it needs to happen?
It doesn't have to be happen. It's a matter of convenience. You don't want to ground it, all right? You can set this potential to any number you like, negative pi square root of 7, I don't know.
What does grounding exactly mean, though?
It means, well, literally, I have a wire, I run outside, and I put that wire in the ground, which makes it connected to the earth, which huge, which means it has, well, infinitely large capacitance. That's what makes the potential of earth normally to be 0. That's how we make this potential to be 0. Yes?
So the V on the top, the R in the middle, the V to the left of it,
120.
that's 120. And then the V on the way right, that's 0. It's still connected.
That I don't understand. Starting from here, V is 120 until it starts changing. And it only starts changing inside a device with a current traveling through.
No, I mean the V on the way right on the top, right?
This?
No, top right.
This?
Yeah, that's 0, right?
Because what?
Because it's still going to connect from the wire to the.
And what do we know about wire? That's it. And because it has no resistance, it does not change potential. Because of the Ohm's law, Ohm's law is the most fundamental law here. It answers all possible questions. If you have an open switch and there is no current through the bulb, I is 0, no potential doesn't change. If you have a current but there is no resistance, R is 0, potential doesn't change. Only when there is a current and resistance, in that case, potential changes. Yes?
In the two parallel ones on the top right, because the total potential is 4.
There is no such thing as total potential. Potential where? If you say potential, you have to say specifically where, at which point.
Oh, so the voltage.
The delta V is the voltage. So you need to practice with matching symbols, words, and meanings. 3 things. If there is some mismatch, that might lead to a mistake. That's it. This is voltage, which is potential difference between potential here and potential there.
So voltage is 40, but then for every individual, so the 2 individual bulbs in there, would they both 20?
What is voltage? What is voltage? The difference. So, and what do we know about wire? And because of that? No, not voltage. The potential. See? So potential, this potential, which was set to 0 out of convenience, that's it, will be 0, 0, 0, 0, 0, 0, 0, 0, 0, up to here, and also up to here. So this electric potential is 0. This electric potential is 0. Now, electric potential here is 40, which means it will be 40 up to here because the wire doesn't change electric potential. And also, and that's what you should be doing, not in your head. I don't know why you still keep thinking, you know it doesn't help. It's a myth. So, if you do what I've done, you see this potential difference will be equal to 40. And if you look at this potential difference is equal to 40. Current, electric current splits where? At the junction here. Electric current, let's make it green. Electric current, those fictional positive charges would travel up to here and then split, not evenly. On the right, we have less resistance than on the left. So the current which goes to the right will be slightly higher. But also this current will split again here. Now evenly. And these are convenient things to see. But that only comes from practice. Yes?
Can we go over a problem with changing currents?
Cannot hear you.
Can we go over a problem with changing currents?
Go. No. All right, 5 more minutes. But you have to give me a specific problem because I don't know what you want to ask about. Specific situation.
So, we talked about how, like, in that one, there was no changing current, so the voltage were equally proportional, so it was easier to have. But, I guess, for example, the changing
You just have to solve a problem when different elements have different R. For example, I don't know, 10 ohms resistor, and now 7. 7 is a bad number because it's a prime number. So you can simplify 7, and let's say 11, another prime number. Now you just have to do what you have to do. Let's say this is 1, 2, 3 volts. Yeah, it's a standard situation. So what do you want to simplify first? This. And now there is no shortcut. You really have to calculate the equivalent resistance. Let's call them 1, 2, 3. So 1 over equivalent for 2 and 3 will be equal to 1 over 7 plus 1 over 11. All right, it's going to be 18 over 77, right? So our equivalent for 2 and 3 will be 77 over 18. Your new circuit looks like this now. Those are actual ohms, so no R's. Now we simplify these, which is easier to do. R equivalent for the whole circuit, which 1, 2, 3, will be 10 plus 77 over 18, wherever it is, 18, 180 to 180.
14.3.
Let me finish. 14.3 ohms. But the circuit now is really simple. So you can calculate 1, 2, 3 volts. Now you can calculate electric current. Electric current 1, 2, 3 over 14.3 point something, wherever it is, 0.9. Now, we need to remember that all these circuits share as the same element the battery. So the current which we have found is the current which goes through the battery, and then it goes through that fictional equivalent resistor. Here, the same current goes out of the battery and travels through that actual resistor, and then it travels through that fictional equivalent resistor. So what can we do right now? Since we already know this current, we can calculate this voltage. Well, probably we need a current. 12 over 14, 8.86. It's 8.6. 8.6, all right. So this will be equal to current times R, 8.6 times 10, 86 volts. Now, for me, the fastest way is calculate this voltage, because I know this plus this equals 123. So 123 minus 86 gives me that voltage, which will be the voltage across these two bulbs. Actual bulbs. And now, since you know the voltage and you know the resistance, you can calculate this current I1, this current I2. You can check I1 plus I2 should give you I. If it checks, everything was correct. So we're going to start the new topic. From now on, anything I say has nothing to do to Monday. Question? Okay. This is an actual piece of ore unearthed somewhere, and this is the experiment. It's a very serious matter. Well, of course, the answer is none of the above, which means in physics we have to name it, we have to study its properties, which means, well, for us, we just have to go to a textbook and read the chapter which says everything about this phenomenon. This phenomenon has a name, magnetism, because, well, historically, this thing was called a magnet. And what do we know about magnets right now is a lot. Let's just take a quick look first at to refresh our knowledge. First of all, this is the natural magnet is very weak. That's why I gotta use very small nails here. But now we can manufacture very strong magnets. You can buy this online, neodymium magnet. See, this is a very convenient thing because you can easily detach it and put it back again. Well, magnets come in different shapes: bar magnet, horseshoe magnet, and we can see what the globe, what it does. It affects a little magnet in a certain way. They all look toward this end, but if I flip the end, now they look away. And that's what differs a magnet from a regular conductor, like a nail, piece of iron. If I have a magnet and another magnet, oops, go away, go away, go away. They always, face each other with a certain ends. But if I have a nail, they're all alive. You see, the nail is being attracted to any end of the magnet. So that's how we can find what is actually a magnet, what is not. And these ends, of course, have been named poles: North Pole, South Pole, because historically first they've been used to travel. And the Earth actually also is a magnet. In general, magnetic field around is three-dimensional, so we can move around, and we can always see where the North Pole is. And if you see, this is the magnet, I know because it's not a nail. It's being attracted only to a certain pole. And if I break it, it's still going to have same two poles. And if I break it again, it's still going to have same two poles. So we cannot separate the poles. Charges can be separated, positive, negative. Magnet cannot be broken into individual poles. Well, there is some theory that it could be done on a microscopic level, but so far it is just a theory. People have been searching for monopoles for many years. So far, nothing. And to describe the property of a space around the magnet, of course, we use the same word, field. But now it's not electric field, it's magnetic field. And what can we do to, well, first of all, to establish the presence of the absence of magnetic field? We can walk around and see. And if we see something acting on it, we say, okay, there is magnetic field here. If it's irrelevant, no magnetic field. and the arrow like that, which is just a regular compass, is used to represent the direction of magnetic field. So when it's in equilibrium, due to friction eventually, comes to equilibrium, the direction inside of a needle from south to north is to be defined as the direction of magnetic field at the location of this compass. As you saw, magnetic field is kind of more complicated than electric, because first of all, rotation means there is torque, but also attraction force. So magnetic field responsible for two things, and that makes things more complicated. So we will try to avoid anything related to forces, only talk about torques, rotational effect. Now, again, where did I connect it? There. A definition. So if we have a compass, we place it, we wait until it is brought to equilibrium, and now we can draw an arrow inside of the compass from south to north, and that arrow is called direction of, we call it magnetic field vector, and we use a letter B for magnetic field, and that arrow represents the direction of B, the direction of magnetic field vector. Inside. What is happening outside? Well, outside, magnetic field lines go out, and no matter how we measure magnetic field, so here, in this region, there is no magnetic field. They all randomly pointing in all directions. In this region, there is a magnetic field pointing in a certain direction. And magnetic field also can be represented by magnetic field lines. To see electric field lines, we used a special device, we called it grass seed viewer. We used the fact that electric field could rotate tiny dielectric grass seeds. Now, if we want to see magnetic field lines, we need to use the fact that magnetic field can act on iron filings. We just need iron file, and to make them move, to allow them move freely, we again put them in the oil, and okay, so now they are randomly, chaotically pointed in all directions. Now I insert a magnet, and we can see magnetic field lines. This is a natural magnet. Magnetic field lines are loops. They go outside and inside the magnet. But magnetic field lines also can be seen around wires of different shape. All we need again is iron filings. They just like tiny, tiny, tiny magnets. Electric field, no, I need a power supply. So I have a power supply, I need to connect it. And now we need to use our knowledge of circuits. Is one wire enough? No, of course not. We need two wires. Second wire goes to my power supply. Let's see, actually I didn't check the supply in the morning. Okay, it works. So let's look at this point. You can see they form circles. So this wire goes straight down, and what we see, circular magnetic field lines around it. This is a very important fact. We're going to use it in the future. And just for the future, again, just take a look at a wire inside a single loop. I need to knock it. Why? To get rid of friction. There's a friction. When I knock it, yeah, they will fly a little. And during that time, when they fly, magnetic field makes them turn. Here. Well, it has been expected. Here we have a loop like this, like this. But a loop also in this plane has such kind of a portion of a wire getting down and then a portion of a wire getting up. So around this portion we have almost circle lines here, and it actually looks like a field of a dipole. But here, that's what we call a solenoid or a coil, many loops together. What should you expect? Well, we just need to combine magnetic field of several loops in one, and you can see that inside the loops, magnetic field points in the same direction. Uniformly spaced lines, that's a uniform magnetic field. And the uniform magnetic field, of course, is the easiest magnetic field to study, because everywhere inside, magnetic field has exactly the same direction and exactly the same magnitude. So we can use that to study properties of it. And of course, there's another, okay, done with this. Another way to generate strong magnetic field, more or less uniform, is using a very strong magnet. The magnetic field between these two poles is almost uniform. And we will use this fact very soon. So what's going to happen if I place several nails? They show magnetic field how does it point? Well, the rule is that to know the direction of magnetic field, we have to use a compass. We have to place it. Now, you don't see it, but I can show you how, well, actually, you see what's going to happen. See, magnetic field so strong, it makes this magnet, oops, you can keep it. It's broken anyway already. So this is the same magnet but bigger. And the red color always represents the north pole of the magnet. The blue always represents the south pole of the magnet. And the rule says magnetic field at the location of that magnet inside the magnet should point from south to north. So where is south? Here. Where is north? Here. So magnetic field between these two poles should point like this, what we call to the right. Which means here, outside of this north pole, magnetic field outside points from north to south. So inside from south to north, outside from north to south. That's what we need to remember. And what helps me to remember is that north is cold. That's why everyone escapes, including magnetic field lines. South is warm. Everybody wants to go to south. So this is a very important fact, how to establish the direction of the magnetic field. And we've seen the pictures. How do I know if magnetic field line points like this? This is how I take a magnet, I place it here, and I wait. That's it. And then I look at the magnet, and I draw a vector which inside the magnet goes from south to north, like this. And then I call it B. This is a magnetic field vector. And this is the magnetic field line. That's it. Here at the middle point of this loop, magnetic field vector points like this. And the difference between magnetic field lines and electric field lines, magnetic field lines don't have beginning or end. They always are loops, circular loop or very, very, very large, like oval loop. That's it. So again, the Earth is the big magnet, and ironically, the south magnetic pole of the Earth is placed at the north geographic pole of the Earth. People confuse sometimes the geographic pole and magnetic pole. Geographic pole is north, but south is magnetic pole. That's why the magnet, when it's outside, points to north, because it looks at the magnetic south pole. Now, to measure the strength of a magnetic field, people use two different units. In the international system of units, we use a unit has name Tesla, and the physicists usually use a different unit, a Gauss, which is just 10 to the negative fourth of Tesla. And how can we measure? Well, we have to study how magnetic field affects on something. On a magnet, for example, or on a wire. We saw 5 minutes ago that a wire generates magnetic field. So a wire kind of acts like a magnet. So if we have a magnet and a magnet, they interact. If we have a magnet and a wire, which acts like a magnet, they also should interact. To check that, all we need is a magnet and a wire. And I have a magnet and I have a wire. All I need is connect the wire to a power supply, plug in the power supply, and turn it on again. Slow motion. I can do it all day. What's happening? We know that if it's not moving, velocity is zero. If it starts moving, velocity is not zero, means there's acceleration, means there's a force. So magnetic field exerts a force on a wire, that's it. And relatively strong, bless you. we can attach a small weight, 10 grams, and still it will be strong enough because this is a very strong magnet. So that's why it's not advisable to use any credit cards, phones, computers close to this. And now what do we do in physics? Well, we measure force, we measure electric current, we measure the length, because we can. And then we analyze the facts. The fact number one: if a wire is parallel to the magnetic field, there is no force acting on it. No matter how strong the current is, nothing will happen. If we change the angle, and we know the direction of magnetic field like this, and we can manage all other parameters. If we change the angle, the force changes, and it reaches maximum value when the wire is perpendicular to magnetic field, like in this experiment. Magnetic field, current. Of course, magnetic field acts only on this part, which is between the poles. No matter how long it's outside, it doesn't matter. It's not affected by magnetic field. And this is actually a definition of magnetic field strength. If we take a wire which is 1 meter long, if we draw a current of 1 amp, and we manage magnetic field which exerts maximum force of 1 Newton, that's what we call Tesla. That's it. And if we have established 1 Tesla, then we can measure all possible number of Tesla, magnitude of any force. And if we measure magnetic field of any magnet, we can use the same expression to calculate the force acting from magnetic field. This expression, again, only works for the maximum force, which only exerted when the angle is 90. And in general, what do we do? Well, let's say we have a uniform magnetic field. So these are magnetic field lines. Magnetic field strength is constant. Magnetic field points to the right. And let's say now my wire is placed at a certain angle. What do? I can always break it down in 2 parts. One is parallel to magnetic field, and second is perpendicular to magnetic field. I can even replace my red wire with kind of 2 green wires. The force will be the same. Now, the force on this part should be equal to 0. The force on this part should be equal to the current times magnetic field times the length of this part. And that's supposed to be the force acting on my wire with the current. So I need a certain angle, let's call it theta, and I can use this triangle, right? Theta. So if I use this triangle, this is the length of the actual wire. Of course, I assume the magnetic field is everywhere. Yeah. So what do I get? L2, that side vertical, should be equal to hypotenuse times sine of the angle between the wire and magnetic field, because this side is the opposite to the angle. So the result is this is how we can calculate the magnitude of a force acting from a uniform magnetic field of this strength on a wire with this length in magnetic field, which carries a current at this angle between the wire and the field. That's the magnitude. What about direction? Well, the direction comes from this experiment. We know the direction in this experiment was up. We know how current travels. We know magnetic field. Turns out that magnetic field, current, and force always related by the right hand rule. This is right hand, right, not left. In this rule, the thumb represents the direction of the force. These fingers, these three fingers, represent the direction of magnetic field. The index finger should point, well, not exactly in the direction of the current, but in the direction of that component of the current which is perpendicular to the field, because parallel component doesn't feel any force. So this is the right hand rule. Always works. Magnetic field, well, we say current, and mean only perpendicular component, the force. That's a rule. So what do we know about rules? They don't require understanding. They require memorizing and practice. That's it. Practice, please. Do you remember this symbol? In PY 105, we used this symbol for a specific direction. In general, we can list several directions: up, down, left, right, out of the screen, and into the screen. This symbol represents what? Into the screen, into the screen. So you have to use your imagination. You have to imagine a long wire, which actually is horizontal, placed like this. An electric current travels away from you into the screen. That's how it's happening. And this arrow represents magnetic field. For example, we can imagine a magnet, and magnetic field line points down. And now you should use the right hand rule to make a statement about the direction of the force. Don't break your rules, your hands, don't break your fingers. It takes practice. And imagination. An ability to visualize things and manipulate with those things in your mind. And it also takes practice. So, what's your answer? Well, so right hand, first of all, right hand. Now, that should be the current. That's already hard to do for me. So what do? I move. That's it. Electric current points into the screen. Magnetic field points down. The thumb points. No, the cross. The cross means you're looking at the feathers of the arrow, which flies away from you. So this is away from you into the screen. That's it. Any questions? This is just an example, and you're going to use more examples. It just, again, I know I'm going to say it several times in the future, but first, this is the right hand rule. All three directions perpendicular to each other. This is a claw. It's not a right hand rule. You can't use it, and people try. It's not going to work. Straight fingers, 90 degrees angles. Of course, you don't have to use a hand. You can take scissors, cut 3 arrows, glue them up together, call them IBF, and use it, rotate it. Now we're going to first answer a question about the magnitude, about the direction, and also calculate the magnitude. For the magnitude, again, this equation actually has a name. it's magnetic force, but people also call it Ampere's force, because the same physicist who gave a name to unit of electric current studied magnetic fields, French physicist, Ampere. So Ampere's force, force acting from magnetic field on a wire with a current. So you do the question, I'm going to do the magnitude because it's easier, right? We just need to plug the numbers in. Is equal to 2 times 2 times 0.15 times the sine of 30 degrees. The angle between magnetic field and there is a rule which you know. If you know what to do, you just do it. If something is missing or something is not clear, you ask a question. So if you have any question, please ask a question. If you don't have any questions, just go forward. So the magnitude will be equal to 0.3. That's the magnitude. To answer a question about the direction, you have to use the rule. For the rule, you have to know two directions, magnetic field, and that thing we call perpendicular component of electric current. So magnetic field is right here in the picture, we can see it. So to apply the rule, you have to draw that direction, which represents a perpendicular component of electric current. In order to do that, probably first you should draw a direction of electric current. So how does electric current point? No. It doesn't go in, it doesn't go out, it doesn't go left, it doesn't go right, it doesn't go up, it doesn't go down. How does it point? I see you want to say something. Like this? No. This is what? What is that? What is this? Well, so what took you so long? Velocity of the electrons. Electrons are negatively charged particles. By a definition, a direction of electric current is opposite of that. So we just studied it, so we still have to remember electric current points in the direction of the motion of the fictional positive charges, which is opposite to electrons. This is the direction of electric current, I. Still have to remember. I perpendicular, well, that's thing which is perpendicular to magnetic field. So now we are ready to do it. This is how should index finger point, and now we should turn the hand so magnetic field points to the right, fingers point to the right. This thumb shows the force into the screen. So now we have answered both questions. Into the screen, again, standard symbol. The direction is into the screen. The magnitude is 0.3. What do we do if a wire has segments, like a bend? We can calculate force acting on each individual segment and then add them up. Net force is the sum of all forces. What if gravity or tension also acting? We should add them up. So this is only magnetic field, but the same wire might float if we balance out gravity and magnetic force. Could have been done. All right. Please answer this question. Now, this is the work of a genius. A real genius invented this. A device for collecting iron filings. Without this device, we would lost all of them. You know how expensive it is? You don't. So you should assume very. Now here, I really want to see the most popular answer. So please enter your choice. Resend. 6th. So 3, 4, 5, 6. 3, 4, 5, 6. 3. No. 4. Protons never move. Electrons move. So the reason magnetic field exerts a force on a wire with a current and does not exert a force on a wire with no current is because electrons are moving through the wire, which means in actuality magnetic field exerts a force on each individual electron, and then the net force makes it move. So magnetic field does act on a charge which travels through magnetic field. And this is how. This force has a name, the Lorentz force. Physics Lorentz introduced this equation. How did we get this equation? Well, we've got the force acting on a wire and divided by number of electrons. That's it. And we get the force acting on a single electron. So instead of electric current, what we have here is a charge of that particle. This is the same magnetic field. Instead of length, we have speed, not the whole speed, only that part which is perpendicular to magnetic field. When particle travels parallel to magnetic field, it doesn't feel any force, exactly like a wire. Now let's take a look at it. These are standard demonstrations. We have actually maybe so it won't anyway. So I have a power supply here, a vacuum tube. This is a prototype of a first TV. Right now LEDs of course replaced it, but if you had a fluorescent screen here and you could manipulate with the beam, you could make an image right here. That's how it worked. But instead of looking at a single dot, here we can see, this is also fluorescent paper. You don't see electrons, they're too tiny. What you see is the light those electrons make when they travel through this paper. This is an electron beam. Too soon. So first we have to generate the electrons. To do that, we need just special coating and heat it up. Electrons get ejected, emitted. Then we have to pick them up with electric field. And we know electric field accelerates charges. If we apply high voltage like here, they start traveling very fast. And then we can apply magnetic field to deflect those electrons in any direction we want, to make them point at any point we want. That's how those TV tubes work. Instead of course, a bar magnet, they used coils to generate magnetic field they wanted to. And of course, when the magnet is far away, magnet generates magnetic field which is everywhere. But here, at the location of the tube, magnetic field strength is weak. But if I make it closer and closer, strength increases, and we deflect the beams more and more. So, of course, stronger field means stronger force, and stronger force means more deflection. And we actually can make them move in circles. Let's see. Did I turn you on? Okay. All right. It's not as bright as this one, but you can see a circle. How did I do it? Well, here I have two coils, and those coils generate magnetic field, horizontal magnetic field, and I can increase magnetic field strength, decrease, and that changes the radius. Also changes period of motion. So I can make it straight, no magnetic field at all, bend it, stronger. Everything just purely due to Lorenz's force. You will be playing with a similar setup next week in a lab. Next week we have one lab. And that's all what I want to say today. So thank you very much. You're free to go. I'm going to have my office hours as long as I leave the room. Cannot hear you.
The exam will be at 9 o'clock.
The exam is 9 to 10:50, but not here. Remember. You don't know? Why? Morse Building, room 101. Check the syllabus, it's on the syllabus.
No, I was awake. I just forgot that it started at 8. So I was like,
Yeah, and I called her 5 minutes ago, this is my daddy. Now is not the time. This is a game.
next thing you know, Jabari's like, where are you? And I'm like,
I gotta bring this again. I was like,
Dude, what?
but then if I do bring this up, it rains so.
I'm going to send an email. I know that sometimes people don't pay attention to the syllabus, so I'm going to send an email.
So the thing is, I was born out like my first thing is being in Boston.
All right, so let me see. I am done with this. So just keep it in the room until because maybe we'll need it because we will use it sometime later. And here. I'm gonna need this stuff. I'm done with this and this. And again, keep everything on the cloud because she will use it.
okay.
your class start?
We have the exam.
Next weekend.
You too.